Hello everyone, and welcome to the show. I'm Max, and this is PQ adic analysis in the Collatz Conjecture, a video series I'm making to accompany my 2022 PhD dissertation of the same name. This is episode 5, Where No Wiener Has Gone Before. Yes, the title is very silly. And the thumbnail shows a picture of Norbert Wiener himself, the namesake of this episode, father of cybernetics and of Wiener's Tauberian theorem, which we'll be talking about in excruciating detail. So, what have we seen so far? So far, we started with the correspondence principle in episode 3. This shows how we can take the study of the periodic points and divergent points of the shortened qx plus 1 map, TQ, and reframe them in terms of the rational integer values attained by the Newman chi-q of z as z ranges over the two adic integers. We've also seen in episode 4 that, contrary to popular belief, even though chi-q is discontinuous as a 2q adic function, we can meaningfully do Fourier analysis with it. In this episode, we're going to combine these two observations and show how to use this Fourier analysis to study the values attained by chi-q over two adic inputs. And the answer comes from a novel non-Archimedean generalization of Wiener's Tauberian theorem that I first established in my dissertation. So Wiener's Tauberian theorem, the WTT or the W's TT, is a classic of 20th century harmonic analysis, simultaneously unifying and generalizing such diverse strands of thought as divergent series, summability methods, asymptotic analysis, abstract harmonic analysis, and the theory of Banach algebras. To that end, Korevar's book on Tauberian theory, which I've given the reference to in the description, is an excellent exposition of all of these. Also, in my humble opinion, the WTT is probably one of the most beautiful results in analysis, certainly one of the most beautiful results that I'll be discussing in this video series. I mean, you can use it to prove the prime number theorem, and that's pretty cool. So, in a certain sense, the WTT is spectacularly simple. I mean, like, just it's the kind of this seems obvious and uninteresting kind of simple. Consider the following. Just see how. Consider the following. The Fourier transform F is a homomorphism of algebras. This comes from the convolution theorem. In particular, it is a homomorphism of algebras in two different ways. The first is that it turns convolution of functions into products of their Fourier transforms, and conversely, it turns multiplication of functions into convolutions of their Fourier transforms. An algebra, recall, is a vector space where we have a binary operation that acts like multiplication. You can get vector spaces of functions often by multiplying them pointwise, or if you have an appropriate notion of integration, by convolving them. So, let's let E star and E cross denote the functions which are the identity elements with respect to the convolution and multiplication operations, respectively. That is, E star convolved with F, either way, is F, and E cross multiplied with F, either way, is F. Then, by the homomorphism property, the Fourier transform of E star convolve F is the same thing as the Fourier transform of E star times the Fourier transform of F. And since this is an identity element, this is the same thing as the Fourier transform of F. So, canceling out, we see that the Fourier transform must send E star to E cross, the multiplicative identity element. Conversely, by just repeating this reasoning, but with the stars swapped with crosses, we then get that F must send the multiplicative identity element to the convolution identity element. Now, let's suppose F has a cross inverse, F minus cross, so that their product is the cross identity. Then, F times F cross inverse is Fourier transform of F convolve Fourier transform of F cross inverse. And this is the Fourier transform of the E cross, which is E star. So this means that these two functions are convolution inverses of one another. So f, the Fourier transform, takes the multiplicative inverse of a function and turns it into the convolution inverse of the function's Fourier transform. Likewise, if we apply f to the convolution of f and its convolution inverse, we see that we get E cross, the multiplication identity, is equal to the product of the Fourier transform of f and the Fourier transform of f's convolution inverse. So, combining all of this, we conclude that just like any other algebra homomorphism, the Fourier transform sends star invertible functions to cross invertible functions, and vice versa. And moreover, the Fourier transform of a cross inverse is a star inverse, and the Fourier transform of a star inverse is a cross inverse. Very simple. And literally, that's Wiener's Tauberian theorem. That's the entirety of the theorem. And let me remind you, this thing is considered to be one of the crowning achievements of 20th century harmonic analysis, up there with Carlson's resolution of the centuries-old problem of L2 convergence of Fourier series. So at this point, I would not be surprised if certain members of the audience probably want to wring me by the throat, which is understandable. The devil really is in the details. The above proof of the WTT is an example of a kind of faux simplicity that can often be found in math. And as is often the case, the source of the problem is due to abuse of terminology. Mathematicians have an unfortunate habit of using the word simple when what the word really mean is clear or clean. So, as an example, David Urbanek of the University of Toronto has a set of notes explaining schemes that early on, like in the second page or something, points out that the entirety of J.C. Maxwell's equations of electromagnetism can be written out as just two formulas. This is the exterior derivative of f is 0, and the Hodge star of d and f is mu 0 times j. I know what the exterior derivative is, but I don't know what the Hodge star is. Anyhow, so some people have the temerity to call these equations simple. These people debase themselves. They might be saying simple, but what they really mean is clear or clean. This is very clean. It's very, very clean, but it's not at all simple. And this is the unfortunate truth that just because something is clean looking, it does not mean that it is simple. So yes, while it is always true that simple things are going to be clean, the converse is not at all true. Clean things are not guaranteed to be simple, and especially in math, will rarely be so. If making something simple requires sweeping all of the details under the rug, like we did with that proof of the Wiener-Tauberian theorem, and you sweep it all on the rug and then you hope your mom doesn't notice all the stuff you swept under the rug, then you're doing yourself and your subject a disservice by calling it simple. The reason why this reformulation is beautiful isn't because it's simple, and it's not simple, but rather that you can take an incredibly complex and incredibly fundamental set of equations like Maxwell's electromagnetic equations, and you can put them in such a clean and compact expression. We're gaslighting ourselves if we think of this as simple, because we're then blinding ourselves to the beauty and sheer effort that gets put into taking complexity and making it compact. It's because, unfortunately, many things in life are incredibly complex, but don't have such simplifications. And we need to be more aware of how we're managing our information, because otherwise we'll lose touch with the details. A case in point, the heuristic argument that I just gave to quote-unquote prove the Wiener-Tauberian theorem obscures the fact that the content of the argument's assertions actually lie in the underlying spaces, the algebras of functions were being used. Indeed, I would go so far as to say that once you've established that the Fourier transform is a homomorphism of algebras in the way I was describing above, then yes, everything we did follows exactly by the pure formal manipulations we did. And the difficulty then is in showing that the underlying, the chosen function spaces possess the correct algebraic properties. Also, it completely ignores the power and beauty of Wiener's result and all of the incredible things you can do with it. So rather than just jump down into the nitty gritty, let's take a little bit more of a more gentle descent into the meat of this theorem. So rather than just consider it in the abstract, let's start by considering specifically L1 of R, the space of Lebesgue integrable complex valued functions on the real numbers. If f and g are integrable and they have the same Fourier transforms, then f and g are equal as elements of L1, which meaning that their difference is zero almost everywhere. This tells us that the Fourier transform is injective over L1 of R. So, writing the L1 norm by this, and all of the absolute values are normal complex absolute values, then Young's convolution inequality tells us that the L1 norm of f star g is less than or equal to the product of the L1 norm of f and the L1 norm of g. This then tells us that the convolution operation is continuous with respect to the topology created by the L1 norm. So we can equip L1 of R with the operation of convolution, and the result is a Banach algebra. The convolution theorem for the Fourier transform is then the assertion that f turns the convolution of two L1 functions into the product of their Fourier transforms. Since f is a surjective map from L1 onto its image, if we can use this to give f of L1 of R the structure of a Banach algebra under pointwise multiplication, and then f is an isomorphism from this algebra to that algebra. And then, as an isomorphism of algebras, it then follows that f sends invertible elements of this algebra to invertible elements of this algebra. Recall that a unit is an invertible element of an algebra, and that an algebra is said to be unital if it contains a unit, and in particular, a unital algebra is one that contains a multiplicative identity element. So, in particular, we have that the convolution of two L1 functions is the multiplicative identity, that is the star identity of this algebra, if and only if the product of their Fourier transforms is the multiplicative identity of this algebra. However, it's easy to show the following. This Banach algebra, also known as the group algebra of R, is non-unital, meaning that it contains, not only does it have no multiplicative identity element, but given any f in L1 of R, there exists no g, such that this is the identity element. Before we give the proofs, here are the main ingredients. If f is in L1 of R, then its Fourier transform is uniformly continuous. And secondly, the Riemann-Lebesgue lemma. If f is in L1 of R, then its Fourier transform decays to infinity at infinity. So first, let's use these two to prove this theorem. By way of contradiction, let's suppose that L1 of R, the convolution algebra, contains some multiplicative identity element, E star. Next, let's just pick some function f. This will be the indicator function for x being between negative 1/2 and 1/2. And the Fourier transform of this is the sinc function, sine of pi xc over pi xc. The convolution theorem tells us that if we assume, as we have, that E star is an L1 function, then this statement should hold, which, using hats, is f hat equals E star hat times f hat. Since, note that this function is non-zero for all real numbers xc, which are not non-zero integers. So for all real numbers that accept the non-zero integers, we get that E star of xc is equal to 1. By this proposition 49, Since E star is uniformly continuous, and this shows that E star hat is uniformly continuous, this shows that E star hat is equal to 1 almost everywhere, and so by uniform continuity, E star hat has to be equal to 1 everywhere. Regardless of this, though, even just by showing that it's equal to 1 almost everywhere, we then have that the limit, as c approaches negative or positive infinity, this limit can never be 0. But that contradicts the Riemann-Lebesgue lemma, which says that if f is in L1, its Fourier transform has to decay to 0. So this means that our assumption that E star was in L1 was erroneous, and therefore there can be no multiplicative identity element in this algebra. So this proves that our Banach algebra, L1 of R with convolution, is non-unital. Now let's prove the propositions we use. So first, we want to show that the Fourier transform is uniformly continuous. So to do this, we're going to let epsilon be our modulus of continuity, and we're going to consider two real numbers, xi and zeta. Since f is integrable, it has to decay at infinity for its integral to converge, and in particular, if we start integrate it from x bigger than r epsilon or less than r epsilon, where r epsilon is really, really big, we can make it so that all of the area under the curve of f between r epsilon and r epsilon is small. So this here, this thing is going to be less than epsilon over 2. And so now we just break things up in the traditional analysis way. We have our integral over the infinity, from negative infinity to infinity. We break it up into the integral in between the r epsilons here and outside of the r epsilons. Here we have this, we bound using the triangle inequality. This is bounded by the product of the L1 norm of f times the supremum of this function. Here, this is bounded by the supremum of this function on the, all of r, and here this is going to be less than epsilon over 2 by our choice of r epsilon. And here we use the standard estimate that this thing is less than or equal to 1 for all real numbers t. And so expanding this, we see that the supremum on this bounded interval is less than or equal to 2 pi r epsilon times xi minus zeta. So putting everything together, we get that the difference between the Fourier transform of f at xi and the Fourier transform of f at zeta is less than or equal to 2 pi r epsilon times the L1 norm of f times the absolute value of xi minus zeta plus epsilon over 2. So since xi and zeta were arbitrary, if we make them satisfy this condition, we then get that this is less than epsilon, and therefore f hat is uniformly continuous. Next, we have the Riemann-Lebesgue lemma. Suppose, as with many things in analysis, for this proof, we're going to start with a function that's continuous and compactly supported, and we're then going to use the fact that such functions are dense in an L1. So let f be continuous and compactly supported, and let's fix a non-zero xi. By the translation invariance of integrals over r, f hat, it's the same thing if we add pi over xi to both x's, and then use the property of the exponential function, this becomes a negative. So f hat of xi is 1/2 times twice of itself. This is one formula for f hat of xi. This is another formula for f hat of xi. And then we get the following. Since f is continuous, so then we have that this limit converges pointwise with respect to x, and it converges to 0. Moreover, since f is compactly supported, so is this difference, and so this integral is bounded by this function, which is integrable, and so by the dominated convergence theorem, we can then interchange the limit and the integral, and we get 0. For the general case, we let f be integrable, and then since, as I said, the continuous compactly supported functions are dense, we can pick a sequence of such functions, fn, which converge to f in L1 norm. And so the difference between f's Fourier transform and fn's Fourier transform is bounded by the L1 norm of f minus fn, and then taking the limits, we get this as desired. And since this proves that the fn hats converge uniformly to the f hats, and since the fn hats are uniformly continuous and uniformly convergent, we can then interchange. Well, actually, not uniformly continuous. Since the fn's converge uniformly to the since the fn hats converge uniformly to f hat, we can then interchange the limits and of with respect to n and with respect to c to get what we want. So the problem with our abstract approach to the WTT, at least in the case of L1 of R, is that we picked the wrong Banach algebra. In particular, the identity element of L1 of R is actually the Dirac delta, the is evaluate at zero functional, and it's a fundamental property of the Dirac delta that when you convolve it with any L1 function, the result is the same L1 function. The theory of what are known as approximate identities is when you take a family of functions which converges to the limit, in the limit, to delta 0, and that then provides you a family that you can evolve with to smooth out your functions and get approximations. As everyone knows, because informally delta 0 is defined as infinity at 0 and 0 everywhere else, it's not a function. And so this is where the problem was. We picked the wrong algebra. Curiously enough, though, anyhow, once we've established that the Banach algebra we've picked actually has the right properties, it's unital and whatnot, and once we've established those analytical facts, everything else follows by pure algebra. So in this case, the hard part of these kinds of proofs and the complexity lies in showing that the objects you are working with have the right analytic properties. Once you do that, you can square them away with algebra where things are much cleaner. Now, curiously enough, there's actually a non-trivial connection between everything we've just discussed and the inverse approach to defining the Fourier transform that we used in episode 4. Both there and here, we can jury-rig Banach algebras with the right properties by insisting that we work with Banach algebras x and y, such that for the Fourier transform f from x to y, x is equal to the pre-image of y, or equivalently, the image of y under the inverse Fourier transform. In this case, we can then get what we want by writing any given f in g in x as the inverse Fourier transforms of f hat and g hat. So this setup, where all of the functions in the domain algebra are the inverse transforms of functions in the codomain algebra, this setup is precisely where we get Wiener algebras from. So, amazingly, even though the statement, if the Fourier transform is an isomorphism of Banach algebras, it sends units to units, even though that statement is seemingly tautological, the Wiener-Tauberian theorem has a wide array of different formulations, some of which, at first glance, might not seem to have anything to do with one another. All of the following, for example, are equivalent reformulations of the underlying principles. So the first, and this was a result that Wiener himself proved, an absolutely convergent Fourier series has a reciprocal, which is also represented by an absolutely convergent Fourier series, if and only if our Fourier series is never zero. The Fourier transform is an isometric Banach algebra isomorphism from the Wiener algebra of R to L1 of R, and if f is in L2 of R, the span of the set of translates of f's Fourier transform is dense in L2 if and only if the Fourier transform of f is non-zero almost everywhere. The protean quality of this theorem actually makes a lot of sense. In our abstract setup, and this is where the clarity gets us somewhere because we can see connections that might not be apparent. In our abstract setup, what we really saw that all we needed was two Banach algebras that were related to one another by a Fourier transform. So that means we have a multiplication algebra and a convolution algebra. Once we have Banach algebras that are related in this way, we get some version of the Wiener-Tauberian theorem, and depending on which pair of algebras we're working with, the result will be different. Indeed, all three of these cases here are different versions of the Wiener-Tauberian theorem for a different choice of algebras x and y. Because of this, it should not be surprising at all that we can generalize the Wiener-Tauberian theorem to the case where our Banach algebras are non-Archimedean. So because I'm still in the business of working out PQ-adic analysis for functions over QP, at the and for the moment, for simplicity's sake, we're going to be working with functions on the p-adic integers. And so at the moment, the PQ-adic version of the Wiener-Tauberian theorem I will have for you today is primarily a result about Fourier series. Anyhow, to give the classical Archimedean version of this result, the Wiener-Tauberian theorem for Fourier series, in other words, this guy, we need to talk about, as I said, the Wiener algebra. So here's a setup which works very generally. So let F be a metrically complete, algebraically closed valued field with an absolute value we'll be denoting by Q. Here, Q is either a prime number or infinity, and if Q is infinity, we require F to be Archimedean, and if Q is not infinity, we require F to be non-Archimedean, and that its residue field has characteristic Q. Then I write W of ZPF. This is the PQ-adic Wiener algebra on ZP, and we define it as follows. If F is non-Archimedean, then this is the space of all continuous functions from ZP to F whose Fourier transforms, in the sense that we defined in episode 4, decay to zero Q-adically at infinity. On the other hand, if F is Archimedean, we require F to be continuous and for its Fourier transform to be absolutely summable. Meaning the sum of its absolute value is finite when we sum it over all elements of ZP hat. It remains to be seen whether or not defining the WZPF in the Archimedean case as uniformly convergent Fourier series. Well, I should clarify. Using this setup, what we have is that when F is non-Archimedean, a function in the Wiener algebra is precisely the one that functions which have uniformly convergent Fourier series. When F is Archimedean, the Wiener algebra is the set of functions that have absolutely convergent Fourier series. It remains to be seen whether or not defining the Archimedean case as being uniformly convergent Fourier series, as opposed to absolutely convergent Fourier series, will produce anything useful. I discovered this on Wikipedia of all places, that apparently there exists a continuous function on the unit interval, it's periodic, with the property that it has a uniformly convergent Fourier series, but the Fourier series is not absolutely convergent, and this is because the function is very, very, very wiggly. So regardless of how we define it, we then equip our Wiener algebra with a norm, Fw. If F is non-Archimedean, it is the supremum of the Q-adic absolute value of F hat over Zp hat, and if the F is Archimedean, it is the L1 norm of F hat. And this then makes the Wiener algebra into a Banach space. And moreover, by the convolution theorem for Fourier transform, the Wiener algebra is a Banach algebra with respect to pointwise multiplication. The Wiener algebra on the circle, W of R mod Z, is all complex valued functions on the unit interval that are one periodic with absolutely convergent Fourier series, and we make that into an algebra under pointwise multiplication. So in this setup, this is exactly the pre-image thing I've talked about. Every function in this algebra can be expressed as a uniformly convergent series, if the field is non-Archimedean, or as a absolutely convergent Fourier series, if the field is Archimedean. So it's important to note that unlike L1 of R as a convolution algebra, these Wiener algebras are unital. The identity element of the Wiener algebra is the constant function 1. The Fourier transform of the constant function 1 is going to be the indicator function of 0. This is supported on a single point, and as a result, it's not only does it decay to 0, but it's in little L1. This only works in this case because ZP is compact, and likewise because R mod Z is compact. If we wanted to try and work with the Wiener algebra over a strictly locally compact field, this would no longer work because there would be the function 1 is not in the constant function. It's not integrable if your domain is not compact. The function 1 is not an element of L1 of R. So that means that L1 of R cannot be a unital algebra under multiplication. So actually this means that L1 of R is not a unital algebra under either multiplication or convolution. And now just a little bit more notation, which will be relevant both in the near future and in the future. So here, let G be an abelian group written additively. Let F be a field, and let G to the F be the set of all F-valued functions on G, and we make this into an algebra under pointwise addition, scalar multiplication, and pointwise multiplication. For this should be a C. For every C in G, I define the elementary translation operator, tau C, as the operator which sends a function f to the function f of x plus c. Note that for any C, this should be a C, not a gamma. For any C in G, tau C is a homomorphism of algebras. Here, alpha and beta are scalars, and f and g are functions. Tau C of alpha f plus beta g is alpha times tau C of f plus beta times tau C of g. Likewise, tau C of f times g is tau C of f times a tau C of g. So that makes tau C an algebra homomorphism. Finally, given an f, I write trans of f to denote the set of all translates of f. And given any subset of S of this space of functions and any field K that extends F, I then write the span K of S. This is the set of all linear combinations of elements of this should be an S, not a G. It's the linear combinations of elements of S with coefficients in K. And here we define this to be 0 whenever the upper limit is less than the lower limit. All of this is a fancy way of saying is that if f is a function and you see a symbol of the form tau C of f of x, this means the function f of x plus c. Trans of f is then the set of translates of f, and then span k of trans of f is a set of all linear combinations of finitely many translates of f, where the coefficients of the linear combinations are elements of K. The version of the Wiener-Tauberian theorem that we're going to be generalizing today comes from the classical result about Fourier series, but we're going to be reinterpreting it a little bit in terms of convolution inverses. So the result is as follows. Let phi be a element of the Wiener algebra on the circle, meaning that phi is a function that has period 1, it's defined on the reals, that has an absolutely convergent Fourier series. Then the span of the translates of phi hat is dense in little l1 if and only if phi of t is never 0. So what we're going to do is the argument that I gave in the beginning, but with the details fleshed out. Then everything will work because we've chosen a Banach algebra with the correct properties. So we start with the fact that W of R mod Z, the Wiener algebra on the circle, is a Banach algebra, and that the Fourier transform is injective. One way to see this is to note that every function in the Wiener algebra on the circle is continuous on the circle and therefore is integrable. So this is, and then therefore we have the injectivity of the Fourier transform on the integrable functions. And so by definition, here's where the jury rigging comes in. We defined the Wiener algebra as the set of all things with absolutely convergent Fourier series. This means that by definition, F ends up being a surjective map, in addition to an injective one, from the Wiener algebra on the circle to little l1. And to see that it's surjective, note that if you have a phi hat in little l1, then the function that we get by summing the Fourier series, this is going to be an element of the Wiener algebra, and its Fourier transform will be phi hat. So in particular, the Fourier transform is going to send units of the Wiener algebra to units of little l1. Now, since the Wiener algebra is algebra's operation is pointwise multiplication, the constant function 1 is the multiplicative identity element. So we're going to start with phi being, actually the thing is, if phi is a unit, then it has a multiplicative inverse such that this occurs, and in particular this forces phi t of being non-zero. Yeah. So to this, if we suppose that phi is a unit, then what we get is that the Fourier transforms of phi and psi, when you convolve them, you get 1, 0. This is the convolution. This is the identity element of the convolution algebra, little l1. So now what we're going to do is to show this density thing. What we want to show is that if phi hat is a unit, which means that this is true, that we then, given any eta hat, we can pick something that we can convolve phi hat with to get eta hat. To begin with this process, let's just notice that if we have eta hat is in little l1, its convolution with phi hat is the following. If we consider this as a limit of sums, we use the translation operator, we get the following. And note that this is a linear combination. If we ignore the limit, this is a finite linear combination of finitely many translates of phi hat, and then the coefficients in this case are going to be in the complex numbers. So in particular, what this tells us is that convolving two L1 function, little L1 functions, is the same thing as considering a limit of linear combinations of translates of one of the little L1 functions. Now, what's important here is that this limit isn't occurring just pointwise. It's also occurring in the topology of little l1, which is the topology induced by the little l1 norm. To see this, let's subtract the full convolution with the partial sum. This then leaves the tail of the series. By definition, the little l1 norm of that tail is this. And now we're going to swap the two sums. This needs to be justified, so that's why I have an exclamation mark. But note that once we've justified it, because this sum is translation invariant, we can get rid of the subtraction by k, and then this turns into a product. This is the little l1 norm of phi hat. And here, since eta hat was in little l1, this thing right here is going to decay to 0 as big K goes to infinity. And since this is bounded uniformly in K, this little L1 norm, this then shows that the convergence happens, provided we can justify this interchange. This interchange is justified by the dominated convergence theorem. Here we're using the counting measure, and our sequence is double indexed as little k goes to positive or negative infinity. And here, these are non-negative, valued everywhere. The sum as k approaches infinity is the sum of the things is pointwise. As k approaches infinity, this is pointwise convergent because it goes to 0. And moreover, it's for any individual k, this function is dominated by the sum, which is convergent because these are both L1 and this is just their convolution. So what this shows is that convolving two functions in little l1 is the same thing as considering a linear combination of translates, and moreover, that the partial sums of those linear combinations of translates converge in little l1 norm to the full convolution. So this is an observation. In particular, if we consider the translates of phi hat, we see that for any eta hat in little l1, phi hat convolve eta hat is going to be in the closure of the span of the translates. So now suppose that in particular that phi is a unit of the Wiener algebra, so that there's some psi hat such that convolving phi hat and psi hat gives us the identity element of little l1. Then that means that the closure of the span of the translates of phi hat contains 1, 0. Now here's where the little trick has. The basic point is that once you have a recipe to convolve phi hat with something to turn it into 1, 0, you can then convolve something with phi hat to turn it into anything else you want. Specifically, given any function eta hat, what we'll first do is we'll convolve psi hat with eta hat, and then since convolution is associative, we can then regroup this, and this, as we saw, is 1, 0, but 1, 0 is the identity element, so this just reduces to eta hat. In other words, once you know that phi hat has a convolution inverse psi hat, to make phi hat convolve a function to give you eta hat, you just need to convolve phi hat with psi hat convolve eta hat. To make this, so that shows that phi being a unit of the Wiener algebra, meaning that that this holds true, which particularly means that phi t is non-zero, that shows that being a unit implies that the closure of the span of the translates of phi hat is dense in little L1. So now let's do the converse. This means that we're going to start with a function phi, and we assume that this span of its translates is dense in L1. We then need to show that phi of t is nowhere 0. To do this, what we'll do is suppose that the span of the translates is dense. Then, in particular, that means that there is a sequence of linear combinations of translates, phi n hat, which converge to 1, 0 in little L1 norm. Now, since, as we saw, in particular, any element of this span, any finite linear combination of translates, is going to be of the form phi hat convolve eta hat, where eta hat is not just any L1 function, it's a compactly supported L1 function, so that we get a finite sum here. Okay. Whoopsies. You should ignore that. So anyhow, we assume that phi hat, it has dense span of translates, and then we pick a sequence of span of translates approximating 1, 0. Then, in particular, this means that there has to be some compactly supported function eta n hat, such that phi n hat is the same thing as convolving phi hat with eta n hat. In other words, what this is saying is that because this, by definition, is a linear combination of translates of phi hat, we can then just figure out what the translates are, and then that immediately gives us our eta n hat. So, and as we saw by this argument right here, we then have that this sequence will converge in little L1 to 1, 0. Since f is an isomorphism of Banach algebras, it's a continuous operator, and in particular, it's going to send the inverse is also continuous, and it's going to send phi hat convolve eta n hat to the product of phi hat's inverse Fourier transform and eta n hat's inverse Fourier transform. This, of course, is the function we call phi of t, and this thing in particular, as n goes to infinity, because this is going to converge to 1, 0, this is going to converge the whole thing to the inverse Fourier transform of 1, 0, which is just 1. That then shows that this product, as n goes to infinity, is going to converge to 1, which in particular shows that this limit converges here. Moreover, this limit is occurring both pointwise with respect to t and with respect to the norm of the Wiener algebra, and then this limit then gives us a multiplicative inverse of this Fourier series, and in particular it proves that this can't be 0, otherwise this limit wouldn't exist. So this shows that the translates of phi hat are dense in little L1 if and only if phi of t is non-zero for any t in R mod z. Yeah. So just to summarize this situation, we have this nice little chart which shows a relationship between a Banach algebra with multiplication and a Banach algebra with convolution in the case where these two Banach algebras are related by a Fourier transform. F is a unit here if and only if its Fourier transform is a unit here. F is non-zero here if and only if the span of the translates of f hat are dense here. The reciprocal of f is an element of the Fourier of the element of A if and only if the f hat has a convolution inverse, and the reciprocal of f is the inverse Fourier transform of something if and only if the reciprocal of f has a Fourier transform that is in B. So, and just in general, we're going to get WTT type results whenever we have isomorphisms between unital Banach algebras. So now an interlude, we're going to get really into the granular detail now. So a great deal of mathematics concerns sums and what they add up to. Then over the years, we've found many, many different ways of evaluating seemingly intractable sums using clever tricks. Stars in this field include Abel, Tauber, and Wiener. So one of the most useful tricks for evaluating an infinite series is the so-called analytic method, which is to reinterpret our sum as the value of an analytic function at a point. One of the most familiar examples is the sum for the ln of 2, which we can obtain formally by writing this power series using the geometric series formula and then integrating term by term to get the identity ln of 1 plus x is equal to this sum, and then we let x increase to 1. In general, it is not going to be in the case that we can obtain the sum by considering the limit of the power series. Indeed, it's possible that this limit on the left can converge even though the sum on the right diverges. A classic example is the Grandi's series, 1 minus 1 plus 1 minus 1, which mathematicians have been debating for centuries. And so this is non-convergent, and yet if we consider the associated ordinary generating function, this sums to 1 over 1 plus x, and the limit as x increases to 1 is 1/2. So in other words, this thing can converge even when this thing doesn't converge. To that end, we say that a series of real or complex numbers is Abel summable to a complex number S if the limit of the power series converges to S. Abel's theorem, proved by Niels Heinrich Abel himself, tells us the condition in which we can be guaranteed that this limit is going to be equal to this thing. And in particular, the conditions are as follows. If the ANs are real, all we need then is that this series converges. It doesn't even need to converge absolutely. Conditional convergence is fine. And so as an example, because by the alternating series test, this series converges conditionally, then by Abel's theorem, the value of this sum will be equal to the limit of its power series as x increases to 1. If the ANs are complex numbers, in addition to having the series converge here, you also need to require that the limit, as z in this case tends to 1, it has to occur in something called a Stolz sector, which is a region of the open unit disk in the complex plane of the following form. The Stolz sector basically looks like the mouth of Pac-Man. So Abel's theorem tells us when we can obtain an infinite sum by considering the limit of a generating function. At the end of the 19th century, Alfred Tauber established a partial converse to Abel's result. So Abel says that that if our series is summable, then its ordinary generating function will converge to the sum. What Tauber found is that if we have a series of real numbers whose ordinary generating function converges at the limit, and if the AN satisfy the condition that they grow little o of 1 over n as n goes to infinity, then we can deduce that the sum is convergent and its sum is equal to S. So the moral here then is, and this is the first in the line of what are now known as Tauberian theorems. A Tauberian theorem is generally going to be of the following flavor. You have some series of real or complex numbers, which when you put them into a generating function and take the limit of the generating function, you get a certain quantity. Then, provided that the numbers in the series satisfy a certain bound of some kind or a certain decay condition, you can then use that to then either get the convergence of the series, or you can, more generally, you can get asymptotic equivalence, meaning that the behavior of this function as x tends to 1 will be equivalent to the behavior of the limit of the partial sums of the series. And a sweeping generalization of this result was established by Hardy-Littlewood. It's called the Hardy-Littlewood-Tauberian theorem. I mentioned this in episode 3.5. And what this allows us to do is it not only do we work with convergent series, we also work with divergent ones. And so here is one generalization of the Hardy-Littlewood-Tauberian theorem. Let an be a sequence of real or complex numbers such that one of the following holds. The ANs are complex, and they are bounded in absolute value. Or the ANs are purely real, and either they're all bounded from below, or they're bounded from above. Then, for any complex constant c and any positive real number omega, we have the following equivalence of asymptotics. Namely, that the limit as x increases to 1 of 1 minus x, the power of omega, times power series. If this is equal to c, that's the same thing as saying that the limit as n approaches infinity of omega factorial, where I use the gamma function to define the factorial, over n to the omega times the sum of n equals 0, n minus 1 of ans is equal to c. In other words, what this is saying is that if the generating function has a singularity at 1, which is of degree omega, then the partial sums of the coefficients will diverge at a rate of big O of big N to the omega. And this can be, you can change from power series to exponential series by making a simple change of variables and here. And so in this case, it's as x decreases to 0. This theorem implies the prime number theorem. In particular, Hardy and Littlewood did this in the 19-teens by showing that the exponential generating function of the von Magnolt function, that's basically the natural logarithm of the Mobius function from number theory, they showed that it is asymptotic to 1 over x as x decreases to 0. That means that the ratio of these two, of the left and the right, tends to 1 as x decreases to 0. This then implies that the average order of the von Magnolt function, that's the limit of the average of the sums, that this equals to 1, and this is equivalent to the prime number theorem. So what this then tells us is that there's lots of really interesting things we can do with asymptotics by passing back and forth between sums of numbers and the singularities of their generating functions. It was with these ideas in mind that in 1932, Norbert Wiener comes along and he writes his paper, Tauberian Theorems. This is how his paper starts. It's like this. Numerous important branches of mathematics and physics concern themselves with the asymptotic behavior of functions for very large or very small values of their arguments. The Fourier integral is of particular interest in this study, in the study of asymptotic problems. And so what Wiener does is then as follows. Letting f be an L2 of R, we then consider the function g of u, which is defined by we take the Fourier transform of f, where we restrict to an interval of width 2a, and then we let a go to infinity. We then know that this limit will converge in the topology of L2, although Wiener uses the older terminology of limit in the mean. And then we have that this function will then satisfy the inversion formula, and again the convergence will be in L2. As he then says, the asymptotic properties of f of x and g of u each correspond to the local properties of the other, meaning that the behavior of g as u approaches positive or negative infinity tells us about the behavior of f of x for finite values of x, and likewise the behavior of f of x as x goes to positive or negative infinity tells us about the behavior of g for finite u. So in particular, there is a large class of asymptotic problems in which the asymptotic property to be investigated is connected in some obvious and simple way with the entire class of functions f of x plus lambda. An example of such a problem is the investigation of the asymptotic behavior of the integral from negative infinity to infinity of k of lambda f of x plus lambda d lambda, many problems on which first investigation do not appear to be concerned with integrals of the above form may be put into such a form by an elementary transformation of variables. For example, if we put x equals log of xc, lambda equals log of mu, f of x equals phi of xc, and mu times k of lambda equals q of mu, then the integral in question assumes the following form. The obvious and simple connection Wiener refers to is a dastardly trick. So we're going to define the following function. K name of x, it's defined by as follows. If name equals Cesaro, we define k of x to be 1 minus x if x is between 0 and 1, and 0 everywhere else. The brackets here are Iverson brackets, our favorite notation. If name equals Abel, we define k Abel of x to be e to the negative x when x is greater than or equal to 0 and 0 everywhere else. And if name equals Lambert, we define k Lambert of x to be 1 minus x when x is 0. So this is going to be 1 when x is 0. And ex over e to the x minus 1 if x is positive, and 0 everywhere else. Then the following delightful thing happens. Consider the limit as x approaches infinity of n equals 0 to infinity of an times k name of n of x. Then, where an's are just real or complex numbers. Then, if name equals Cesaro, this limit is equal to this. And if name is equal to Abel, the limit is equal to this. And if name is equal to Lambert, the limit is equal to this. These names, incidentally, refer to different summability techniques. In particular, we say that an is Cesaro summable if this limit converges. We say it is Abel summable if this limit converges. And we say it is Lambert summable if this limit converges. By a simple change of variables, this is the same thing as the limit here that we saw in for power series. And so what we've just done is we've rewritten this limiting process on this left-hand side. We've rewritten it as a limit of this form. Now this formula might seem a little bit random, but actually it isn't. Here, this is n, and then we have n over x. This thing is a convolution with respect to multiplication and a counting measure. And in particular, it is a simple matter just by the definition of the Riemann-Stieltjes integral. By definition, this sum is equal to this integral, where a of v is by definition the summatory function of an. Whenever I work with the Riemann-Stieltjes integral, I always need to open up the Wikipedia page to remember the formula, to rewrite them, but because it makes my brain hurt working with the details. But anyhow, if we make a change of variables, we then end up with the following. And using Abel's summation formula, if this func k name of v is sufficiently nice, we can then move the little d from the a to the k, and we get a derivative, and we get this. And so what we've done is we've taken this thing without the limit and rewritten it as an integral. And so in particular, note that as x goes to 0, we get the following. This a of xv disappears and just becomes a of 0, which is then our desired sum. And so what's happening here is that by having converted this into an integral, this constant here is the constant of proportionality, the main case being here. So it's really what we're looking at, it's analogous here, is that if the ratio of these two things is equal to 1, then the ratio of these two things is equal to 1, and the same thing is happening here. If the ratio of these two things is equal to negative a of 0, then the ratio of this and these functions here, which diverge, is going to be equal to 0 as well. As for the versions that Hardy and Littlewood discuss with these powers of omega, you can get these simply by modifying this function slightly, multiplying it by certain other factors to change it. And with that trick, you can then reformulate all of these summability methods in terms of the asymptotic behavior of these integrals. Now, because the k function here is something we integrate against, in order to transform a into something else, the tradition of analysis demands that we call k a kernel. If we make an exponential change of variables, v equals e to the u and dv equals e to the u du, and set big K of name equal to the negative derivative of little k of name evaluated ln of u, we have the following. Obviously, if the ANs are, say, all positive real numbers, then for any x greater than 0, as u goes to infinity, this is going to be a big number. This is going to be an even bigger number. So this thing is going to get very big as u goes to infinity, which makes this non-integrable. However, here's the trick. Look at the k that we were working with. All of these functions, these two cases, this case it's compactly supported, and in these two cases, our function is integrable because of the decay of this and that. As a result, we can instead consider we pass off the integrability or compactly supportedness of the kernel to a, and so we can define, for example, f of u comma x is equal to this function if the k name of u is non-zero, and is equal to 0 if k name of u is 0. And so in the Abel case that we were originally in the Cesaro case, for example, then this works and it's compactly supported and everything's nice. And so what we end up getting is that this function here is going to be either compactly supported or integrable, thanks to its interaction with this guy. And so instead of considering how k name works when we integrate it against this particular choice of big A, we can understand the kernel k name better by considering its Fourier transform. Then, by taking linear combinations of the complex exponentials of these Fourier transforms, we can then use these these coefficients to approximate A and then get what we want. And so in this language, the Wiener's Tauberian theorem is actually a characterization of these kernels, k, for which we can deduce asymptotic information about the series, in particular about the ANs, by considering the asymptotic behavior of the integral. Yeah. So what this, in particular, this says that the kernels are the k's that are the nice functions such that this conclusion holds. In this case, Tauber's O of 1 over n condition is then going to be generalized to a condition on A. And in practice, one condition that always works is when A is slowly oscillating, by which I mean that this limit occurs. The property that K is nice is then the what we saw above. For example, in L1, this would be the requirement that K's Fourier transform has no zeros. If this was being considered in the topology of L2, we'd be using the case that K's Fourier transform is non-zero almost everywhere. And so in this way, we can see how these two seemingly unrelated problems of asymptotic equivalence can actually be transformed into limits of integrals and then studied using Fourier analysis because everything just happens to work out nicely. At the moment, I'm actually trying to reverse engineer all of this stuff in the p-adic context, basically by studying a p-adic Mellon-type convolutions, but this has been frustrating for me because, unfortunately, unlike the Archimedean counterparts, the p-adic Mellon transform is much more difficult to compute and doesn't have easy closed formulas like the gamma function integral. Anyhow, so all this is really amazing and it's wonderful, and in this language, as I said, the Wiener-Tauberian theorem tells us which kernels are good for making these kinds of asymptotic analysis. This is, not only is this very interesting, it's also incredibly useful because, as we just saw, the Hardy-Littlewood-Tauberian theorem proves the prime number theorem, and the Hardy-Littlewood-Tauberian theorem is a simple consequence of Wiener's Tauberian theorem when you work with Wiener's Tauberian theorem in this setup. So all of this detail, this beautiful, amazing detail, was contained in the seemingly obvious fact that the Fourier transform is a homomorphism of algebras, and an isomorphism if you pick the algebras correctly. That's an example of where the cleanliness, the clearness of the big level result, the abstract, masks all of this incredible detail. And I think it's a shame just to say, okay, Wiener's Tauberian theorem is trivial because it's just about algebras. No, there's all these amazing things we can do with it.